So last time we did, we're doing this half section thing going, but we did the rest of 2.1 and half of 2.2, right? And then you had homework due, which will be due tonight, over 2.2a. And then 2.2b will be due Wednesday night, along with 2.3, provided I get as far as I think I'm going to get today. All right? So any questions over the first kinds of graphs that we went through? We're coming up with a pretty long list of different graphs, and I'm not going to really talk a whole lot about some of them, and there'll be a paragraph in the book about, a different kind of chart. They don't really show you how to do every one, but you should know how to interpret them, know what they are, okay? So I forgot to turn on the projector. So the projector is going to take a little bit to get warmed up, but...
So 2.2a is due tonight?
Right.
And then 2.2b is due Wednesday?
Right. 2.2b and 2.3. 2.2b for sure. 2.3, hopefully, will be due Wednesday. So 2.2, the second part is just a few additional graphs that we haven't talked about. And then I have a PowerPoint slide that has the different graphs, just a summary of all of them with a little blurb about each one. So we'll just talk about those. Then we'll jump over to 2.3. And so based on your data, the remaining types of graphs that we need to talk about, I've made examples of in here. So this is what's known as a stem and leaf plot, or you'll hear it referred to as a stem plot for short. And notice that the plot itself is made out of numbers, whereas we talked a little bit about a dot plot, and I'll show you another one of those. And then we've done histograms and bar graphs and those kind of things. The problem with a histogram is you lose information. You take all the pulse values or the height values or whatever, and you just count, well, how many fell in this range? And the bar just says how tall it is. All right? So how many there were. The stem and leaf plot, the bars are made out of the numbers from the data set. So it's a handy graph. You can recapture the original data just based on looking at a stem and leaf plot. One of my favorite kind of test questions over this is to give you a stem plot, have you make some conclusions based on it about the shape of the distribution and all that, but then say, enter the values into your calculator and compute the mean, the standard deviation, the median, the mode, all those things. All right? So you can recapture the whole data set. So the way this works is you divide each number into two parts, the stem and the leaf. Generally, you'll use the last digit, the last significant digit in the number as the leaf, and then the rest of it is the stem. These are ages. So what I did, it doesn't work great for a really big sample size. And so what I did was I took a random sample of 30 subjects out of the 365 total subjects. Understand what I'm looking at here? So a random sample. So I got a sample of size 30. Now, these are their ages. So ages are two-digit numbers. So if I make the last digit the ones place and the tens place, I didn't really say that right. If I make the ones place the leaf, then I can make the tens place the stem. And the way you do it is you draw a line that separates the stem from the leaf. Now this one is produced by software, and it's upside down of what we would normally create. So I'm going to draw most of this the other way around. It doesn't really matter. It's just interpretation. But I like it flipped the other way. So small numbers, 1, 2, 2, 3, 3, are at the top, and it comes down. All right? So I'm going to write it that way. So I'm going to start with one line for each stem. Notice this one's been broken into two, which is acceptable. And if you've got enough data, it helps to split it because it gives you more bars, basically. Okay? So the way this works is the tens place together with the ones place is an age. Okay? So this right there is an 18-year-old. Then there's another 18-year-old. And another 18-year-old, a 19-year-old, and so on. What about this one? What's that? 27. That's a 2 and a 7. So there's one 27-year-old in this sample of 30 subjects. Right? One 30-year-old. What about this one? Read those to me. Hey, you got it. 50, 52, and 54. Yeah.
Okay, so the stems place is the tenth place, or the stem is the 10th place?
It is in this data.
Okay.
So she's asking a question, is it always the tens place? No, not always. One of the examples that they do in the book, they have numbers of salaries. So they might have 22,500 and 45,000, numbers like this, right? And they say, well, the last two digits are always zeros in this particular data set. They rounded to the nearest $500 for salary. So they forget about the last two digits. They make the 5 the leaf and the 22 the stem. So they stress it in the book, and I'll stress it now. You need to put a key on there so people can figure out what the numbers mean. And they do, in this book, they do a better key than what the software did. Interpret this for me. Multiply stem dot leaf by 10 asterisk asterisk plus 1. What? What is that saying? Well, it means take the stem, a decimal point, and a leaf, so 2.7, multiply it by 10 to the first power. So take 2.7, multiply by 10, you get 27. Here's a better way to make a key. And this is how they do it in the book. 2 stem 7 equals 27. So on a test, if I put a stem and leaf plot on the test, I would put a key like that at the bottom of it. Right? What would the key be for this one? 22 stem 5 equals 22,500. And then that orients the reader that, 22, they're rounded to the nearest 500. Right? Okay? And then you just go through your data, and every time you come to a value, you figure out, well, what stem does it go on? So my data, as soon as I hit 44, then I say, well, let's see, I got to find the one with a 4, and then it goes right there. Right? Now, to do one row per each stem, like I wrote here, what would this first row be? 8, 8, 8,
9.
And 6 nines? Nothing changes, right? The next row would be what? 1, 2, 3, 4, 5 zeros. 2 ones, 2 twos, 3 and a 4, and a 7. See it? If you're only going to have one, that's everybody who's in their 20s. And you list them all out. Yeah?
So, like, how do you know if you're supposed to split it into, like, two different ones?
Great question. Did everybody hear that? She said, how do you know if you're supposed to split it or not? It's just the same exact decision when you're making a histogram and you're trying to decide, well, how many bars should I make? It's personal choice. It's which one shows the data better. If you've got lots of data, then you can split it. That's not the split one. You can split them like this and show by splitting this, it shows that, almost all of the 2's are in the low part of the 2's and hardly any in the high part of the 2's. So you have this extreme skewness to this distribution. Right? So it's just personal choice. Right? And it's almost always either 1 stem per number or 2 stems per number. It's pretty rare you'll see them go 3 per number, although people do that, but it gets confusing on how you split it. How do you split it here? Which ones go on the lower one and which ones go on the higher one?
1 through 5.
Nope, not 1 through 5. Good guess, but look at the 20s. 0 through 4s go on the first one, then 5 through 9s go on the second. Okay? So it's the same way you would round. If it's 5 or higher, you're going to go up. If it's 4 or lower, you're going to go down. Okay? Now this, since all of the numbers on a particular stem are in order, it's called an ordered stem plot. When you're going through a data set by hand and you're marking them, they won't be in order. You might hit a 2 before you hit a 1. Right? And that's an unordered stem plot. Most of the time the software will always order it, but if you're doing it by hand, you might not. Now, if you are doing it by hand also, you need to be very careful about how you space the numbers out. Use the same amount of space per number, otherwise you get a distorted picture of what's going on. If I did my 2's by scrunching my 0's real close together because I had 5 of them, then all of a sudden 5 numbers here takes the same space as 3 up there, and it doesn't look right. Right? It's distorted. Right? The whole idea is to get a picture of the shape of the distribution. And the reason I like this kind with the small numbers at the top and the big numbers at the bottom, rather than the way my software did it, is because you can stand over here, turn your head, and go, oh, looks like a histogram. If you do that here, it's a backwards histogram. Right? It's hard to mentally flip that. So, tell me about the shape of this distribution. Look at the stem plot. What kind of shape does this distribution have? You have to look at this one, but flip it. Is it symmetric distribution? Is it bell-shaped? Skewed. Good. Which direction? Skewed to the right or skewed to the left? You said both. You can't say both.
To the left.
I got 1 vote for the left. Which way is the skewness? It's the way the long tail points. So this is skewed right. Right? So this is skewed right. That's part of actually section 2.3, shapes of distributions. But skewed right, the tail points right. Skewed left, the tail points left. And it's really hard to remember which is which. But you get to have a cheat sheet. So make sure it's on your cheat sheet if you struggle for, I can never remember which way that thing points. Okay, any questions on stem plots? What's the advantage of a stem plot? What's that? Okay, what kind of details?
The numbers of the data.
Exactly. The actual numbers are there. Whereas if I made a histogram out of this, all you see is a bar. You don't know, you know there's 10 people in this row, but you don't know what their values are. They might be 20, they might be 29, you don't know. But a stem plot uses the numbers, so you preserve the original data. Okay, let me scroll down and let's talk about dot plots. This is data out of our old textbook, but this is sodium content of cereals, breakfast cereals. Right? So why do you think they call it a dot plot? Because they're dots. Duh. Right? It's a dot plot. So what you do, sometimes to make a reasonable looking dot plot, you need to round the numbers. But the dots will stack up. You just put a dot at every value that you have on a number line. So you just make a number line that'll span the range of the data. Put a dot wherever you have values. Now, if I collected sodium to more than, notice everything's been rounded off to the nearest 5. If I had a 123 and a 126, they would both round to 125, but the dots wouldn't stack up, right? So you do a little bit of rounding so that the dots stack up and look nice, and it gives you, again, just an idea of the distribution of data. So dot plots are pretty simple to produce. Again, they work great for small data sets. They don't work very good for huge data sets. If I gave you our spreadsheet with 365 observations and said make a dot plot out of height, you'd be there a while. You got 365 dots to put in there. Okay. I think I showed this to you last time, did I? I showed it to one class and not the other. I guess it was the other one. This is known as a time plot. The book calls it a line graph. It's another name for it. So a line graph is a graph where the x-axis, remember algebra class that you had to have to get in here? The x-axis, the x variable, is time of one sort or another for a line graph. The y-axis is whatever value you're measuring. So a time plot is something that's being measured across time. What I'm measuring here is the percent of people in our samples each semester that said they smoked. Right? So the first, looks like the first semester that I collected the smoking data was in the fall semester of 2003. That's like 12 years ago. And I've collected it every semester since. Question?
Is this always time?
It will always be time, but that term time doesn't have to be like what you could measure on a stopwatch or a calendar or whatever. It could just be, this is the first one, this is the second one, this is the third one. Right? So there's some order to them in the way they've been collected. If I'm working in the Pepsi bottling company, and I start taking measurements through the day, or taking samples of bottles to make sure they're getting the right fill height, then I just say, well, this is the first one I drew, this is the second one I drew, or whatever, right? But so something that indicates the progression is your x-axis. And what you're looking for is trends. Do you see any trends in this data? Has the smoking rate changed over the 12 years that I've been collecting it? Yeah, it's a definite trend. It's a trend in the right direction, too. Right? There's a lot of variability semester to semester, so it bounces around a lot, but overall there's a general downward trend. Right? That's a good thing. Here's a time plot for the percent who exercise across time. Notice with this plot. This one's having the opposite. So people are exercising more and smoking less. Right? Wait, that's not what I hear on the news every day. What I hear on the news every day is how fat Americans are getting. Right? We're getting a higher and higher percentage of people are obese every year. But what's the difference? Why does our data show something different? The population. We didn't sample adult Americans. We sampled mostly college kids. Right? So at least college kids are getting healthier. I like that. This is the annual mean monthly temperature in Lawrence, Kansas from 1857 to 2002. This is a line graph, or also called a time plot, or a time series, as you'll hear it called also. What do you see here? It's getting warmer, isn't it? You have to look at the axis to see how much warmer, but again, there's a lot of variability year to year, so if you just kind of think of looking at the middle of the bandwidth, back in 1857, it was about average annual temperature of about little more than 51 degrees, and in 2002, average is about right there. That's about 55 degrees. So we've gone up about 4 degrees in that amount of time. Doesn't sound like that much, does it? But it's a very clear trend. You think it's going to slow down and stop? No. What the scientists are telling us is that it's actually an exponential shaped curve, and it's going to start getting a lot warmer real quickly. And when it does, we're all going to die. So do something about it. Okay, so here's a quick summary of the different kinds of graphs we've talked about. Pie charts, what did I say about pie charts? I said I hate them, right? But you should know what you're looking at when you see them, because you do see a lot of these. But it's just, pie chart is only appropriate when you have all of the categories that could happen, right? So, we did health rating. And that's everybody, right? The whole sample would be, but if you ever have some kind of a variable where not everybody in the sample makes one of the wedges, then you'd have a missing piece to your pie, and it wouldn't make sense to do one, right? But the size of the slice is the percentage of people who fall in that particular category. A bar graph is just a bar that gives the height of either the frequency, the number of people in that category, or the percent of people in that category. We talked enough about those. A Pareto chart, I don't know, did we talk about a Pareto chart? Okay, a Pareto chart is just a bar chart that's been rearranged so the bars are tallest, next tallest, next tallest, so they're decreasing, which just for your eyes sorts it so you can see the most frequent category was this one, right? Now, it only makes sense with categorical data. Even ordinal data, you can't do a Pareto chart because there's already an ordering to them, and it doesn't make sense to go rearranging that. But for purely categorical, like what kind of car do you drive, then you put the tallest bar on the left-hand side and say, well, most people drive this kind of car, right? Then we talked about side-by-side bar graphs. We showed 2 different ways to do it. This is one where you have, this might be smokers and non-smokers side by side. Then in the next category, smokers, non-smokers, and so on. A stacked bar graph is the same idea, but instead of putting them side by side, you lift one up and set it on top of the other one. So you stack them up. That gives you not only the relative difference between the groups, but also what's the total if I add the groups together, right? Forget about whether or not they smoke. What percent of people said they were a 3 in health? Then the stacked bar graph gives you that. Okay. I'm not going to teach you how to make these kind of graphs, but I put them on a test. Just put one there for you to analyze and make conclusions off of it. Okay, here's a histogram. We've talked plenty about those. And a frequency polygon. Did I give you frequency polygon last time? Okay, a frequency polygon really is just a bar graph, only instead of drawing a bar, you put a dot at the top of the bar in the midpoint. And then you connect them with a line. So it's really just another way to represent the same thing. I went looking on the internet for an example of a frequency polygon, and I found this. Right? This is finishers in 30-minute segments as a percent of the total in 3 of the biggest marathons in the United States. So this is the Marine Corps Marathon, which is in Washington, D.C., Chicago Marathon, which is New York City Marathon. And it's just the percent of finishers in, so these are the percent of people who ran 2 hours to 2 hours and 30 minutes. 2:30 to 3 hours. 3 hours to 3:30, and so on. Understand? And then the dot is just what percent of people finished in that range. And then they just connect them with a line. So it looks kind of like the line graph we were talking about, but it's called a frequency polygon. It just shows the frequencies, but it makes kind of a polygon out of it instead of a bar graph. Same thing. I could have done this same graph with a bar graph, but it would have been more difficult to display because I got these 3 marathons trying to cram all in there together. Right? This makes it easier to put them all. And you see that they're really similar. All 3 marathons are pretty similar. So. Okay. Ogive. That's how you say this. Ogive. An ogive is a frequency polygon, only instead of plotting the relative frequencies, you plot the cumulative frequencies. So they go up. They're strictly increasing graph. And they show you, okay, like if I do an ogive of heart rate, then down at 40 it would barely be a blip because we only had one of those. But by the time I get to 72, I should be up at about 50%, right? About half the subjects have a heart rate of 72% or less. And it just keeps going up until you get all of the data. And then we just talked about stem and leaf plot. And let's see, I guess we've talked about dot plot. Retains original data by plotting a dot above the data value. And the line graph, put down in your notes that this is also called a time plot or a time series. They do say that in the book, but that's what I'm used to calling it, so that's probably what I'm going to call it on a test or something. But line graph, time plot, same thing. Got it? All right, any questions about the different types of graphs before we jump into section 2.3? Yeah?
How do you know which graph to use?
Well, that's a good question. How do you know which graph to use? Let me ask you this. For a categorical variable, like what kind of car do you drive, can I do a histogram?
No.
No? How about a dot plot?
Maybe.
No, can't do a dot plot. A dot plot is for quantitative data only, right? Because you have to have a number to put above the number line, right? To put a dot above the number line, you have to have a number. So you could put the categories under the number line and stack dots up, but that's technically not what a dot plot is, right? So a lot of it has to do with what kind of data that this particular graph is appropriate for. And then if you have more than one choices, like should I do a pie chart or should I do a bar graph, those are both appropriate for categorical data, then it's just a matter of personal preference. But if you do a pie chart, then I'm gonna flunk you. Just kidding. But that's a good question. But notice, I thought it said in each of these boxes what kind of data. Well, some of them do, I guess. Like this one says, a histogram of quantitative data. Right. So. All right. So we've talked about different shapes of distributions. Let's finish that discussion, and then we're going to talk about kind of good and bad graphs and analyzing different graphs. Let's see. I want to minimize that. And let's just go. So if you have a distribution shaped like that, what do we call that shape? What'd you say? Okay, the bell curve. This is bell-shaped and symmetric, right? So bell-shaped and symmetric. And what does the word symmetric mean? What's that? I know what you mean, but I'm gonna say no. It doesn't mean evenly distributed because we have a distribution. Evenly distributed to a statistician means all values are equally likely, so it's flat or horizontal, right? But what you mean is
If you fold it together.
good. If you fold it over, then one side lays on the other side, right? So what about a distribution like this? Is that symmetric? Yeah, it's symmetric. It's not bell-shaped. It's anything but bell-shaped, but it is symmetric, right? This is what we would call bimodal. Guess what that means? It means two something. Two modals. Well, it means two modes. And what's a mode? We haven't actually talked about mode yet, but that's in chapter 3. Good. Data values that occur most often. Well, if there's two of them and they're separated, then you might have bimodal data. There's two modes, right? There are some examples of data that would be bimodal. They're a little bit hard to come up with, but one I like to use is, think about when you were in middle school, did they have the father-daughter banquet like they do in Holton? Okay, well, just go with me. You go to a father-daughter banquet, right? And you write down the ages of everybody there. And then you make a histogram out of those ages. What's its shape going to be? Well, I guess obviously it'll be bimodal because I'm using it as an example of that. But how would you know that if you read that on a test? You'd get a hump for the daughters, and they're going to be humped around. What's middle school? 6th grade? How old are 6th graders? I don't even know. 12. Okay, you'll get a hump around 12. Right? There'll be a few 11-year-olds, a few 13-year-olds, but most of them will be right in that area. Then there'll be a big gap, and then you get the dad's ages, right? And so a father of a 12-year-old would be, what? Yeah, 40, 30, 35, 40, somewhere in there. So you get a hump around 40. The hump for the dads would probably be a little wider than it is. I mean, you're pretty set on ages in middle school. But for fathers, you know, there's no rule. You got to have a kid by this date. Right? Okay, so that's symmetric. This kind of distribution is called uniform. And that's the one that Emily was trying to say they're evenly distributed, but this indicates that any value is equally likely as any other value until you get to values that aren't possible and aren't possible. Right? So a good example of this is, think of the last 4 digits of your Social Security number. What the government tells us is those are random digits between 0 and 9. So if I pooled all of your 4 digits together, we'd have a sample of, what do we have, 30 people, 25 people in here, times 4, I can do that one, 100. I'd have 100 numbers, right? Well, approximately 10 out of the 100 would be each of the 10 digits. They should be pretty equally distributed. It is symmetric, but it's definitely not bell-shaped. It's uniform. Okay? And we've talked about skewed to the left and skewed to the right. Those are basically about all the shapes that you'll encounter. You can get U-shaped distributions and other things that are just, they don't really have a name. They're just, you will encounter them, but most of the time, you're going to get something that's either uniform, skewed left, skewed right, or bell-shaped and symmetric. Even bimodal is very rare. You don't see that in practice very often. Okay, so let's talk about analyzing graphs in section 2.3, and basically just what makes a good graph and what makes a bad graph. And so I'm going to use some of the author's pictures. And the authors use this as an example of a good graph. And it's too small to read here, but it says source. Remember the argument we made back in earlier chapter about consider the source? Right? So deciding whether you got a good graph or a bad graph, a lot of that just comes down to where they get the data. Right? If the data is not trustworthy, then the heck with the graph. But this is generational divide over American exceptionalism. And it's funny because I was reading the book, and they say, that's a great title. It tells you exactly what's going on. I'm thinking, I don't even know what that means. It's not telling me what's going on. American exceptionalism. Well, then you read the subtitle, percent saying U.S. is the greatest country in the world. Right? So they just did a survey, and, do you believe that the U.S. is the greatest country in the world? You don't have to answer, but that's what the survey said, right? So then they divided the people into groups based on what generation they're in, right? So, what are you guys, millennials? Not even sure what that means, but...
No.
Millennials are born after 2000, is that what a millennial is? Okay. So you guys are Gen X, right? Generation X. I don't even know what that means either, but I've heard those terms a lot. And then a boomer. That's me. And actually, the term baby boomer came from when the guys all came home from World War II. So then their babies were born in the mid-40s to mid-50s, and I wasn't born that early, so it's only recently they decided to start including people born in the 60s. I don't know how that's from the World War II boom, but anyway. And then silent. What's the silent generation?
They're dead.
Yeah, they're dead. That's a good one.
You said silent.
So I don't know what the silent generation is either. But it very possibly means they didn't identify themselves as one of these. So they were silent on that issue. Who knows? But it's kind of interesting. If you look at the percentages, what do you notice? The younger you are, the less you believe that the U.S. is the greatest country in the world. But other than that, it is a well-designed graph. I like that they put the numbers on the bars so you don't have to eyeball down to some axis and figure out, oh, that's about 48. And it just tells you that's 48. Right? I like that. If there's room, that's a good thing to do. There's not always room, but we talked about those things. Then you will have some homework questions that ask you to identify, is this a cross-sectional graph or is it a time series graph? Time series graph is the line graph that they talked about a minute ago. And basically it's showing something that's occurring over time, or is it showing something that was collected at one point in time? So the question about whether you believe the United States is the greatest country in the world, that was a cross-sectional graph. Just at this moment in time, they asked this question. They didn't go back and keep asking them the same question every year to see if they changed their mind. That would be a time series. Right? A pictograph is a bar graph that uses pictures or objects instead of bars. These drive me crazy. All right, you see them in like USA Today and Time Magazine and stuff like that. But it's very, very common to do the graph this way. And this says incorrect pictograph. What's wrong with it?
You can't tell whether you're backwards.
Yeah, well, you can't over here. This one is correct. These houses are all the same width. These houses get wider as they get taller, so they're just a bigger picture. Well, what does your mind do when you see that happening? It exaggerates the difference between them because your mind sort of does area. Ooh, this is way bigger than this little one down here. But it isn't that much taller. And it's only the height that's depicting the value. So the only thing that matters is the height of it. So they shouldn't be making them wider. Pictographs are just usually a bad idea. The scaling of graphs has a lot to do with the picture that you're presenting, right? So look out for a graph that's scaled properly. And here's an example. The authors of the book didn't put this in there. I put this in there. Governor Brownback has been known for twisting the facts a little bit once in a while to make a point. And his argument, have you heard the stuff that's been on the news about Kansas teachers? And the Brownback administration said that Kansas teachers make more than their Missouri counterparts. And then the people over in Missouri said, that ain't right. And all the Kansas teachers, no, that's not right. So then they kind of refuted the data. But this is about teachers' salaries, K through 12 teachers. You can't read these numbers, but this is a time graph, right? Because this is 2010, 11, 2011, 12, 12, 13, 13, 14. Looks like salaries are going up pretty quick, doesn't it? Now, it's not big enough for you to see the point I'm trying to make here, so I just have to tell you. But what's that number on a graph? 0, right? No, that's 28,000. This is 28,500, right? Actually, this one's 29,000. So if they had drawn this to the right scale, it should start at 0 and go up to the tallest one here. Looks like 30,000, about 400. Then it would look like this. Barely any difference between them, right? But if you want to make it look like more is going on, then you lop this thing off right there so that it expands and it exaggerates the difference between the years. There's definitely, you can't dispute that these numbers are getting bigger. Maybe you can dispute where you got the numbers, but you can't dispute that they're getting bigger, but it's the scale. This thing should be drawn coming up off the floor, right? And then you'd see, well, that's not that big of a difference. This graph shows the minimum wage rates across time. So it starts at 1938 and goes up to 2009. Right? Looks like a fairly steady increase, right? But if you pay attention, look at the numbers. 1938, 39, 45, 50, 56, 61, 63, 67, 68, 74. What's happening? They're jumping around. They're not evenly spaced. Sometimes there's as much as here's a 81 to 90. There's a 9-year jump there, and a lot of them are only 1-year jumps, right? So they say that back in exercise number 10, after the section, they have the graph the correct way. And what you see is that it stays flat and then it jumps, right? So there's big jumps in it. So that's when Congress will pass a new law, that thing will jump. Right? This kind of hides that. Okay, let me see what else I'm forgetting. We talked about outliers before, right? So we had the one outlier in pulse, somebody that had a pulse of 124. Data that falls outside the normal shape of the graph. It doesn't really fit with the rest of the data points. You would consider that an outlier. I think all of this we've done using our own data. I stuck in the age histogram. Okay, so let's see. I've got a few minutes left. Let's I didn't pull up the ebook before class, and it takes me a little while to get logged on to it. So I'm just going to grab some problems out of the end of that section and give you some examples of what you're going to encounter when you get to the homework. Let's see. For each set of data described below, discuss the most likely shape of its distribution. All right, everybody understand the game? Here we go. The weights of the defensive linemen on football teams in the Big Ten Conference. What do you think that distribution would be like? The weights of defensive linemen.
Is the scale going to be like 0 to like 300 pounds?
It's whatever you want it to be.
So that way it's going to be skewed right.
If you drew it from 0 to 300 pounds and stopped at 300, but we need to go far enough to get everybody. You think there's any defensive linemen more than 300?
Yeah.
Probably, but probably not a lot more. Maybe 350, right? So, but it doesn't have to, even if you draw it from 0 to 350, you can still get normal and bell-shaped if there's room for the tail off of wherever the hump is. But what do you think? What's that? I think so, which is what you were saying. I think that most of them would be clumped near a really high weight. But you're going to get some that are quite a bit lighter, but you're not going to get any that are quite a bit heavier. Why would you not see a 450-pound lineman? Because now to weigh that much, they're going to have to be way overweight. And they're going to be slow, and they're going to be, right, they're not going to be a good athlete. But you can get 300 pounds just by being 6'8" and massive, right? So they're probably going to hump up near a number up near close to 300, but you'll get some defensive linemen that are quite a bit lighter. Maybe even clear down to, I don't know if you get to 200, but you think somebody could be a good defensive lineman if they were only 200 pounds?
No. They're almost.
If they were all muscle and super, super fast and just really tricky, maybe so, right? Maybe so. So but they'd be outliers. There would only be a few that could do that. So you have outliers in one direction and not in the other. Okay, math scores on the ACT of a large randomly selected group of high school seniors. Math scores for high school seniors. What do you think? Think it'd be bell-shaped? Yeah, I agree. It's probably bell-shaped. If you did math scores for actuarial science majors, right? High school ACT math score for people who later decided to go into actuarial science, a math major. What do you think those would look like? Skewed to the left. They're going to be, the people who are really good at math are going to be the ones that go into that major. They're going to tend to be up near the hump, or up near the natural wall of a perfect score, and then you'll tail off the other direction, right? Lengths of pregnancies of a group of gorillas being studied in the wild. Lengths of pregnancies.
Bell.
I'm hearing bell. I'm hearing skewed to the left. What's that? It would not be uniform. Uniform, I've raised it, but remember, uniform means that any value is equally likely, right? So it's going to be bell-shaped and symmetric, because the average, just to think about humans, not gorillas, but the average is 9 months, right? Or 41 weeks, I think is what it is. So you're going to have, most people are going to be pretty close to that, but you'll have some that go a little early, some that go a little late, but being way early or way late is going to be pretty rare. So it's going to tail off. But it's not going to just chop off suddenly, right? Last 4 digits used to generate telephone numbers. That'll be uniform. Income levels of a group of, well, this says professional baseball players, but let's just say income in general. Income, what do you think that distribution would look like?
Bell.
She said bell, he said skewed to the right. It will be skewed to the right. Why do you think it'll be skewed to the right?
So some people that are way more rich than everyone else, and those big outliers going to the...
Very good. There's going to be people that are way richer than, or make a lot more money than most of us, and there's a natural wall at 0, right? You can't make less than 0. Unfortunately, if I make this 50,000 and this 100,000, and then 10 times that distance would be 1,000,000, right? 10 times 100,000 is 1,000,000. So 1, 2, 3, 4, 5, so on. Most of us are going to be humped right around the 50, right? The U.S. household income median is a little less than 50, so I drew a little too far. But then there's going to be this really, really, really long tail going out that direction. So incomes are just always skewed to the right. All right? You feel good about it? Not about income, about statistics. All right, we'll see you on Wednesday.